Hey everyone, and welcome to Dr. Abu at an Academy channel. Today we are going to discuss part 1 of seminar 5 at the University of Debrecen and the Biostatistics subject. In this seminar we are going to discuss the continuous random variables, the probability density function and the cumulative distribution function. So we're going to discuss the density function and distribution function cumulatively, And also we're going to discuss the normal distribution, or what you call it, Gaussian distribution, the definition of it, and the normal density and distribution function. Also we're going to discuss the standard normal distribution, and we will answer some of the examples. So as you can see here, this video is not the distinct variables, it is continuous random variable. So any number can take any value, like the height of the person. We can say the height is 160, 160.1, 160.2, 172, 172.5, 0.13, 0.15, and so on. So it's continuous random variables, So here we'll start with the probability density function, PDF, probability density function. Here is called density function, but it's a probability density function. So here the definition that if I have any random variable, continuous random variable, this continuous random variable here denoted to it by zeta. It could be x, y, whatever. So zeta, x, y, whatever. If I have variable and this variable has some probabilities of happening, probability 0.1, probability 0.2, probability 0.3, and so on, So if I have function which controlling all this probability, so if I'm talking about function of, not function of the variable, function of its probability, the function of its probability. So for example, I said function of x equal anything, So if I get this function, for example, x squared or something, So this is a function of the probability, not function of the values, but function of the probability. So if I have at certain point, I can get the probability of this item. So here, as we can see, if I have zeta, continuous random variable, then it has the probability called density function, Density function, This is the probability density function, whose integrate between two limits, a and b. So let us assume I have two limits from a to b. Give the probability of zeta, takes the values between a. So this will give the probability that the zeta value will take any number within this cluster, between this a and b. That's the probability of the continuous random variable to assume all the values between a and b. So here I'm looking at the area under the graph, under the curve. The area under the curve, I can get it by the integration, If you remember, when we took the integration, if we said the integration of fx, for example, and fx was equal fx equals x squared, for example, fx equals x squared. So the integration of fx equals integration of x squared, which equals x cubed divided 3. In reality, there was one constant here plus c, but if we have boundary limit here and a and b, so c, it will be cancelled. So we have one time, this was b minus the same x cubed divided 3 plus c, also with a, so c will cancel each other, So in this case, if we have a and b, we don't put the constant c. So the function of x, integration of function x between a and b equal the integration of function x squared, equals x cubed divided 3, and put the value between a and b, So it will be, every time I substitute b, x by b, then minus, I substitute all x's by a, So this is called the integration, So here, in order to get the area under the graph, any area under the curve, it will be the integration of the function of the curve. So to make it easy for the student who did not study mathematics in the high level, so the probability under the curve will be the area, The probability will be the area under the curve. In order to get the area, we have to get the function of the curve and make integration for it, There are two characteristics here of this density function graph, that the total area under the curve equal 1. All the area here equals 100% 1, The second thing, that the probability of any specific value equals 0 factorial. If I want one specific value equals 0 factorial. Okay, so here looking at this one, so if you can look at this highlighted area, this area between A and B, okay, between A and B. So just from A I draw a line up until I reach the curve, and from B I draw a line up until, so I want this area. This area, because it's a curve, I cannot calculate, it's not trapezium. I can split it into rectangle and the triangle, but it will not be accurate. That's why we use integration, okay, in order to get an accurate area. So the area will get it by integration, and the area here which is shaded means the probability of x greater than or equals to 60 up to x greater x less than or equals to 80%. Okay. So here these graphs give us the probability of x taking any value between A and B. Okay. So the probability of theta, okay, that x takes the value between A and B, it would be this area. So coming to the next slide, which is the cumulative distribution function. This is called CFD, CDF. CDF means cumulative distribution function. Okay, here we'll talk about density function only. Okay, DF, density function, the probability. So here it was probability. Probability density function, okay, PDF, and here we're talking about the cumulative. Cumulative means that everything before it has to be adds up, okay. Cumulative, say today you earn £5 or $5. Tomorrow you earn 10. So the total you have now 15. 5 from yesterday and 10 today. Day after tomorrow you earn 20. So you will have 15. The cumulative which you have now 15 plus the new amount 20. So you have 35. Then if you get another 15, so 35 plus 15, 50. So every day you have cumulative. So all the previous savings has to be added up. The same thing here for the cumulative distribution function. So the cumulative distribution function, fx of a random variable zeta, okay, at any point x. If I want to get the cumulative distribution function at any point x, this is x, okay, at any point x means it doesn't mean the distribution at this exact point. If it is cumulative, this means the probability up to this point. All the probabilities up to this point. It is not only at this point. It is up to this point, okay? So cumulative, okay, if I graph here, cumulative up to this point. So all the area here before it. It is not this area only. No, all the area before it, okay? If I want the cumulative up to here, so this will be all the area up to this x1. If I up to x2, it has to be all the area before it, okay, up to reaching it, okay. So the cumulative distribution function fx of a random variable at x represent the probability that random variable takes values less than or equal to x. So all the values less than or equal to x. So if I get here, it is not only this point, it will be all the values under the curve until we reach this point, okay. If I want at this x, so it will be all the values until I reach x, okay. So it will be all the values less than or equal to this x. So there are two differences here which we have to identify between this cumulative distribution function graph. If it is cumulative, so the values of x from 0 up to 100%, okay, and the values of the cumulative frequency, because the cumulative property, cumulative frequency, as we said, it cannot exceed, it's a probability cannot exceed 1. So it will be from 0 to 1. So maximum will be 1, and here minimum will be 0. It has to, so cumulative has to be from 0 up to 1. It cannot be more than 1. But if you look at the frequency, at the probability of density function here, the density function, it is not from 0 to 1. It takes readings, okay? It takes readings. It is not up to 1. X up to 100%, but the density function, it is not up to, the density function, which is fx, is not up to 100%. In the case of cumulative, it will be up to 100%. So the good thing in this graph, that you don't need to do the integration and the dirty work, or what the difficult work which we have, the differentiation, the integration, and such work. In this cumulative frequency, you have the data already there. So for example, if I want to say what is the median, okay, the median always happening at only 50%. Okay, x, the value of x should be 50%, half of the midway, okay, 50%. So I come at x equal 50. So this is the line of x, okay, this is x. So I come at x equal 50% here from 0 to 100. I come at x equal 50% and I draw a line. Then automatically I get the probability. The probability is 50%. So what is the probability of zeta being less than or equal to 60? I come at 60, okay, and draw a line, and then I touch the graph or the curve. Then I come here and take the reading, which is almost 0.7577. This is a calculation actually, okay. So what is the probability of zeta less than or equal to 80? Less than, not more than, less than. So I come here 80 and draw a line until I touch the curve. So everything before 80%, which would be, I don't need to calculate all the integration of this area, because this cumulative frequency function is giving me the integration result automatically, okay. So just I'll draw the line. The only thing which I'll do, I'll draw the line from 80. From 80 I'll draw a line and take the reading from here. It is 0.9786, okay. So what is the probability of zeta equals 60? This is cumulative. Cumulative doesn't give the probability of one single point, okay. The cumulative distribution gives the probability of before or after a range, okay, between two values. So at 60%, I cannot say it equals all the items before. I cannot say it's equal 0.75777. It will be equals to 0, okay, at one point, because this is 1 point. But the probability less than 60, so less than 60, all the area less than 60, which I can get from the graph, okay. So this value of the function get the probability less than the number which I given. So here x, I can get the probability of less than this amount, okay. So here the probability at the line 50, this means the probability which is less than or equal to 50. I can get all the area here, which I can go to directly from here. Up to 60, I go with the line up and get the probability of the area before less than or equal to. If I want to get the probability between a range, like this example, the probability of zeta greater than or equal to 60 or less than. So the greater than or equals to 60, where is it on the graph here? Okay, greater than or equal to 60, let us highlight it. Greater than or equal to 60, which is this area. Okay, all this area which is greater than or equal to 60 up to 100, okay. So less than 80, okay. So I need another color. So okay, less than 80. So where is the overlap? The overlap is this area, okay. This is the area between 60 and 80, between 60 and 80. So how to calculate this area? This area equals to the probability of all this area up to 80, okay, for x less than or equal to 80, which all this area, minus the probability of 60, okay, minus the probability of 60. So I end up with this area. Is it clear, or shall I draw it a different time? So in order to get the probability of this range between 60 to 80, I need to get this area between 60 to 80. How can I get this? I can get the probability of all this area up to 80. Up to 80, it gives from 0 up to 80, all these things, okay? And then I get the probability up to 60. 60, up to 60, from 0 to 60, okay? Or less than and equal to 60. Less than and equal to 60 up to here. So I subtract this from it. So I end up with this area, which will be my answer, okay? So the probability of this case, it will be the probability of 80, the biggest one, the probability of up to 80 here, the big one, minus this probability up to 60, minus this one. So the probability up to 80, which was 0.9786, minus the probability up to 60, which was 7577. So this is the probability. Okay, the probability less than 80, as we said, it will be all this area. Okay, I hope this is clear. So here, coming to the main part, which is the normal distribution. Normal distribution is given by this big formula. Okay, so forget about this formula now. The graph of the normal distribution. Normal distribution, always it is drawn like a bell shape. Okay, you know the bell. We have the bell and in the church or in the common places, historical places. So this bell, it's like bell shape. Okay, but bell shape could be bigger, like this one, like this shape. Okay, sorry, could be bigger like this shape, and could be sharp like this one. Okay, so we have different way to draw the bell. So how to draw this bell? Here I got the characteristics of the normal distribution graph. The first thing, that the normal distribution graph produced the familiar bell-shaped curve. This is the bell-shaped curve, and this one also the bell-shaped curve. Okay, the two parameters of the distribution are the mean and the standard deviation. So the mean in the graph, I have to draw the mean. Okay, and the mean will be the same point of the peak of the graph. So the peak of the normal distribution shall be at the mean. So I know that this is the mean. So this should be the peak. Okay, so the peak comes at the mean. So this is the location. So if the mean is here, so the curve will come like this, will come here. So the peak will be here. So the peak always with the mean. So the two parameters here are the mean and the standard deviation. The standard deviation, if I say here, see, this is the mean of the two curves. This is the standard deviation. One standard deviation here, which is very small because this curve is small. But the standard deviation for this big curve, it might be bigger. So if the standard deviation is small, I find the curve sharp like this. If the standard deviation is big, I find the curve is extended flat like this. Okay, so whether it is sharp or flat, it depends on the standard deviation. But the location of the peak, it depends on the mean. So here the two parameters which I have of the distribution is the mean and the standard deviation. Mean called mu for the population, and the standard deviation called sigma. This is for the population, not sample. Okay, so mean, before in the sample we use x bar and this, but in the standard deviation for the population we'll use, instead of x bar we'll use mu. Instead of s we'll use sigma. Instead of s we'll use sigma. Okay, so the two parameters here are the mean and the standard deviation. Mu, the mean identifies the position of the center, position of the peak. Okay, so if the mu is here, this is mu, so the peak will be here. Okay, if mu is here, the peak will be here. So the position of the peak, it depends, it will be at mu. So the position of the mu will define the position of the peak. Okay, so mu identifies the position of the center or the position of the peak of the distribution along the x-axis. Okay, so mu here along the x-axis, if it's here, it says that the peak will be here. If the mu is here, so the peak will be here. If the mu somewhere else here, so the peak will be here. Okay, so mu identifies the position of the center or the peak of the distribution along with the x-axis, while sigma determine the degree of flatness, whether it will be sharp like this or it will be flat. Okay, it is very, very widespread. Okay, flat. The degree of flatness or peakedness. So here it is sharp or peakedness. Okay, like it has a sharp peakedness. Okay, peakedness means sharp or flattens. So what will determine this? The standard deviation. Okay, sigma will determine the degree of flatness or the beacon, the height and the width, okay, of the graph or the distribution. Because these two characteristics, mu, the mean, and the sigma, are the two main characteristics which define everything in the graph, okay, in the normal distribution graph. So that's why mu is often referred to the location parameter. So this parameter define where the mean will be. The mean will be here, or the mean will be here. So the peak will be here, or the peak will be here. So the peak always associated with the mean, okay? So if the mean move, the peak will move with it. If I have the mean here, so the peak has to be here. This is mu. But if mu was here, so the peak will come here, okay? So the peak always move, or the graph moves with the mu on the x-axis. So that's why it's called the location parameter. So mu identifies the location of the graph. The graph will be here, or the graph will be here, because it depends on the mu. Where is mu, okay? Called the location parameter. And sigma often referred to the shape parameter, whether it will be sharp, okay, beaconedness, or it will be flattened. So now, why this normal distribution is important? Normal distribution, this is a graph which can help us to predict the probability of happening of the things, okay? The importance of it in the science of the biological science, that it relates to many parameters, like the weight, the blood pressure, the height. It can be modeled through, so I can make model for them and have their normal distribution. Once I got the normal distribution graph, I can use it to predict, for the cases of the weight, for the case of the height, or the case of blood pressure, I can use to predict the probability of happening, okay? So the normal distribution graph, it will never touch x-axis, okay? It will touch y-axis at the peak, okay, at the peak. So it has only one peak. So I have 5 characteristics for the normal distribution. What they are? The first thing, that it has only one peak, okay. They are symmetrical. So the left side symmetry to the right side, they are symmetrical, okay. They are symmetrical, and their symmetry line is the mean, mu. The symmetry line is mu, the mean of them, okay? The value which they can take from x equals infinity, minus infinity, to x equal infinity. So here you can see it is very close to x, but it will never touch x-axis, okay? It will go and then as parallel to x-axis. So it takes x values from minus infinity to x equals infinity. So any value we can get it, large values, okay? So the first thing, we have one peak. The second thing, we have symmetry line, which is mu. The third thing, that it takes the value between minus infinity and the infinity. The fourth thing, that the maximum value of the curve happening at mu. This is the maximum value of the curve. And the last thing, that the mean, which is sum divided the count or the number, and the median, the middle point, and the number of most repetitive one, the mode, all of them are equal, okay? So the 3 things start with M, called 3M. The mean, the median, and the mode, all of them are equal, okay? These are the 5 properties or characteristics of the normal distribution graph. As we said in the previous slide, that the normal distribution is specified by two main characteristics, which is mu and sigma. Mu and sigma, okay? So let us see here the mu. I have the mu here, 0, mu here equals 0, okay? Mu 0, mu 0. So when the mu equals 0, this is the line, okay, of the mu. Let me do it in red color. That's a more straight one. Okay, so this is the mu. See the first graph here? This is a very weakenedness, very thin, very slim graph. This means the standard deviation for it is small. See the standard deviation for it? What is the color of this graph? This graph is blue color. See? If you look at the key, the standard deviation of it. By the way, this is not the standard, this is the standard deviation square, which is the variance, okay? If you look here, this is the variance. So this is not the standard, this is the variance, sigma square variance. If you want to get the standard deviation, sigma only, so we have to get the square root of it, okay? Square root of it will give us the standard deviation, okay? So if we get the square root of 0.2, we'll get the standard deviation. But anyway, this one will give indication, because if it is a big, it's a square root also, it will be a bigger number. So let us erase this one. Okay, so for this blue color one, the standard deviation, the square of it, the variance is 0.2, small. But if we look at the red one, see the red one? It has the same mean. The mean here also is mu. So the location of the two graphs, see, the location of the two graphs are around the mean. So this is the mean, mu, okay? But this one is more flattened. See, it's more flattened, the red one. More flattened, because its standard deviation is big. Okay, the standard deviation is bigger than this one. Okay, so it becomes more wide, more flattened. Okay. Let us look at the standard deviation. If the variance is 5, which is more than 0.2, and more than 1, it is 5, which is very big. So the orange color. Okay. So how it look like? See, it is more flat. It's almost going to be horizontal or flattened, okay? And all of them around the same mean, which is 0. If we move the mean, so here this is the effect or the impact of the sigma. So if the sigma increase, it will be more flattened. If the sigma is small, it will be more sharp, okay? Or more peakedness, okay? So if we move the mu, see the mu, we moved it to -2. So here the whole graph will move to -2. See, the whole graph moved, shifted. So this is called the location. That's why it's called the location parameter. If you remember here, we said this one will call the location parameter, because it defines the location. And sigma, the shape parameter. See the shape here, the shape changed. It depends on the sigma. The shape changed. Okay? But with the change of the mu, the location only will be changed. So as we said, the area will be equal to 1. So if it is large, its peak will be down. Okay? If it is slim or thin, the peak will be high, because the area equals 1 under them. So if we concentrate the area here, it will be high. If we make it flat, it will be low. Okay? It will be low. Okay? The y-axis reading will be low. As far as become bigger, y will become low. If it comes thin, the y-axis reading will be more, okay? Then coming to the cumulative graph, you remember we have the cumulative graphs here in the previous slides here. I think this was the one. Yes, this was the cumulative. So every time it is increasing, value is increasing, cumulative distribution. So it is cumulative. If I said 60, it's everything before 60. If it said 80, everything before 80. This is cumulative. This is the same thing which we have here. That this is the cumulative distribution graph. Okay, cumulative distribution function, CDF. Okay, so for the cumulative at mu, so every time, see the value every time increasing. See, when x increase. It will never decrease, okay? Until it reaches 1, then it will be constant at 1. Okay, because maximum will be 1. We said the cumulative, for the cumulative, the maximum will be 1. Cumulative, okay? The maximum is 1. So until it reaches 1, then it will be fixed after that, okay? So at mu, the mean, the value of the value will be equal to 0.5. The value of the distribution function, cumulative distribution function. The value of it will be 0.5. So if I take it at mu, the reading at mu, I find the value of the CDF, the cumulative distribution function, equals 0.5. As far as x increased, it will increase. X increased until x reach infinity, which is impossible. It will reach 1. So it will always will be very closer to 1, 0.09, 0.9999999, until it reaches infinity, it will be 1. Okay? The distribution function, the cumulative here should be mentioned, cumulative distribution function approaches 1. Okay? It go towards 1. Keep increasing until it reach 1. See, the value is increasing until this cumulative reach 1. When x approach 1, as x approach to the infinity. I hope this one is clear as well. So here just I want to highlight 2 points. Normally when we have our normal distribution, we put our mu, okay, which is the first characteristic. Let us assume the height of the people in one country or one place. The height of the people is 170, so this is the mu, and the standard deviation is sigma is 8. Okay, so the standard deviation, if we take one sigma from this side and one sigma from this side, it represents 68% of the population. So here one sigma and here one sigma. So it's called the standard deviation. So standard deviation, okay, we'll take one from this side and one from this side. This for one sigma. If in case of 2 sigma, we'll take 2 sigma from this side and 2 sigma from the other side. So if I said I want x, the probability of x greater than 180, okay, or equals to 180. So I come here on the x-axis and check this. The mean is 170, okay, 180 is here. So this is the area which I want. So I have to get this area. How I can get this area? I cannot get it. This area I can get it if I have standardized or standard normal distribution, which is the international table. It is available in the computer program and it is available in the international tables in the book. And you'll be given a copy of this table in the exam. So, but this is not a standard, this is our normal. So what is the difference between the normal distribution and the standard normal distribution, which we have here? A standard normal distribution, the mean must be 0, okay? And the standard deviation must be 1. So if we can convert our graph here, the normal distribution, to standard normal distribution, standard normal distribution, so we can use the table, international table, the standard table which we have. But if we have our own normal distribution, our own problem, we cannot use it. So from here, get the process. If we have an example like this or a problem like this, how to convert it and use it, how to standardize it, how to convert its mean, which is 107, to convert it to 0, and to convert its sigma or its standard deviation into 1. Whatever the value of it, I have to convert it into 1, and whatever the value of the mean, I have to convert it into 0. So the standard normal distribution, always the mean equals 0 and the standard deviation equals 1. And by the way, when you draw the curve, just for your info, not to lose any mark, because this curve should not touch the x-axis. Okay, so be careful when you draw it. Don't make it touch. Maybe the professor will deduct 1 mark from you because you make it touch. It should not touch x-axis at all. So when I want to draw this graph by hand, I just go here and I draw the peak of it to make sure that there are symmetry, and then take it here, and before reaching x-axis, just make it like this, okay? Regardless of how long you, but show that it doesn't touch it, okay? So here, the normal distribution, mu equals 0 and sigma equals 1. So how to convert this? I'll give you an example now in order to avoid going through this theoretical explanation. One example will make it clear to you. In this example, what is the probability a randomly selected adult, okay, of American male is taller than 180, okay? And they have given us the mean. In this example, they have given us the mean 176.3, and they have given us the standard deviation of it 7.1. These are givens in the problem itself, okay? So they have given us the mean and the problem. So when I draw the normal distribution curve, so this is the mean, my mean, mu equals 176. So this is the mean, and my standard deviation 7.1. So from the question here, he said that what is the probability that the random selected America is taller than, more than 180. So I come here at 176, 180 is here. So 180, and check the area which is more than more than 180. So this should be the area. But I cannot calculate this area. I don't have the integration. I cannot spend hours to calculate the area under this curve. So how can I get it? It is easy. The formula said if you want to convert anything to the standard normal deviation, deviation or standard normal distribution. If you want to convert it into standard normal distribution, the only thing what you have to do is, if you have x, okay, value, just say minus mu divided sigma. Deduct from it mu and divide by sigma. It will call a new name z. So it will not be anymore x, because the standard deviation, the standard normal distribution is using z. It doesn't use x, okay? So in order to convert it into z and you get it from the standard normal distribution table, we have to convert it into z. So how to convert it to z? Again, you have the x minus mu divided sigma. So it will be z. So let us see, this example will make it very clear to us, okay? So here I write what I want. I want the probability of a person x greater than 180, right? What I have to do, I just keep the probability as it is, the probability of just in x minus mu divided sigma. Greater than as it is, I will not change it, okay? I leave it as it is. And here, since I said minus mu divided sigma, I have to do the same thing here, okay? In one side, left side, I said minus mu divided sigma, I have to say here also minus mu divided sigma, same thing. I cannot do in one side and leave the other side, okay? So, the only thing which I have to do here is to say minus mu divided sigma. And here also, 180 minus mu divided sigma. So, what is the mu? So, I replace this x minus mu divided sigma, I said this called z, so I called that z, okay? And replace it with that. Greater than. 180 minus mu is 176, okay? And sigma is 7.1. So z is greater than 0.521. Then I can go to the standard normal distribution tables, the standard table, the international table, and go to the graph. It will be the area which is more than 0.521. Okay, I go here more than 0.521, and I can see from the table how much is it, and I can get the answer from there. So here I convert it into the standard normal distribution, not the normal distribution, standard normal distribution. I hope this example is clear. I give you another example to make it more clear and make sure that you have understood it. Of course, this area, okay, the area which you will get from the table will be the area up to here, up to 0.52. But we don't need this area. The area which we are looking for is the area after it. So it will be 1 minus this area. Okay? So the area which we are getting from the normal distribution graph is the area up to the number. Okay? So it will be the area up to 0.521. It will be the area from 0 up to, or from minus infinity up to 0.521, up to here. But I don't need this area, I need this area. So I can say 1 minus the probability which I'll get from the table. So this would be my answer. This is the second example which I'm talking about. What is the probability of a randomly selected adult American male has the height between 170 and 180? The same mu which we had in the previous example, it is the same 176.3. This is mu, okay, and my sigma was 7.1. Okay, 7.1. Okay, so I write what he wants from me. He wants between 170 and 180. So this is my deviation, my mean, okay, 176. He wants from 170 up to 180, okay, 180. So you want this area, okay? So I need to convert them. I just write it x greater than 170, this is what he wants, and less than 180. Then for each x, minus mu divided sigma. So I come here, x minus mu divided sigma, which will be replaced by z, so it will be z. Also here, minus mu divided sigma. Minus mu, which is 176 divided sigma, and here 180 minus mu divided sigma. So this will be z, and this will be the value. So I have to get from, now it's convergence, z appears, so now I can get it from the standard normal distribution table, okay? The standard table of the normal distribution, okay? I can use it. Now, so I go to the table and get for minus or negative 0.887, okay? So it will be all the area from the table. I get the area up to here, okay? And I'll get the area up to here. So I have to calculate the area in between them, okay? The area up to here, okay? So I can get the area. If I use from the table 0.521, I get the area up to 0.521. Then minus the area up to 0.521, this area, okay, up to here, minus the area which is up to minus 0.887. This also I get from the table, so I get the two area. This total area up to here, because the table gives us from minus infinity up to here, I can get the table up to here, minus this area, so I end up with the probability. I hope now it is clear how we can convert our normal distribution graphs to a standard normal distribution graph. So now you can understand this formula, okay? So z equals x in x minus mu divided sigma. Just to standardize that, just sigma x, I have to subtract mu from it and divide it by sigma, okay? The last thing about the standard normal distribution, that for the standard normal distribution, I have the graph. You can, okay, let us use the existing one, okay? So this is my mean, okay? This is my mean value, mu, the mean. If I take from this mean 1 sigma this side and 1 sigma this side, so it will be 2 sigma, total 2 sigma, okay? Because some people confused and said that it's 1 sigma. It is 1 sigma from this side and 1 sigma from this side. So total 2 sigma. But in order to avoid confusion, just we are using that we have 1 sigma here, 1 sigma, and here we have another sigma, 1 sigma from this side. So if we take 1 sigma from here, so this should represent 68% of the population which I have, okay? So most of them, 68% of the population has to come in this 1 sigma from this side and this sigma from this side. If I extend this to 2 sigma from this side, let us use different color. So 2 sigma from this side and the 2 sigma from this side. Okay, of course it has to be from down here, but I don't want to confuse you with the segments here. It is already written here. Okay, so we can use it. Okay, sorry, it is written here already. So here, 1 sigma from this side, from the mu, and another 1 sigma. So here it will be positive sigma minus sigma, because this is 0, should be 0. Okay, and then the standard normal distribution should be 0. So here 1 sigma from this side and minus 1 sigma from this side. So this area represents 68%. Okay. If we expand it to 2 sigma from this side and 2 sigma from this side, it should represent 95%. That's why they are calling it 68, 95, 99, okay, percentage. These are the 68, 95, 99. So if we used 1 sigma from each side, it will be 68. If we use 2 sigma from each side, it will be 95. If we use 3 sigma from each side, it will be 99. Okay, it is more than this. It is 99.7 actually, but approximately they get 68, 95, and 99. Okay, so but if you want to get the exact one, it is 68.2. The other one is 95.4, and the third one is 99, not 0.6, because he is not increasing 0.7. Okay, so these are the exact numbers of the using 1 sigma, 2 sigma, and 3 sigma from each side. So 1 sigma means the total is 2 sigma. 1 sigma from that side and 1 sigma. If you are using 2 sigmas, so it means 2 sigma from here and 2 sigma. So total 4 sigmas, but we are calling 2 sigma from each side. 3 sigma also. So 99.7% of the population will be covered. Okay. So this is called density function. Okay. So density function means the normal distribution. Okay. If you say distribution function, not density function, distribution function means you want to say cumulative. Okay, the cumulative. It's called distribution function. Okay, so this one is the cumulative. This has nothing to do with the cumulative. Okay, so the cumulative, the only thing which we have to know from here, that in case of it change it to standard normal, so we said at the mean it will be 0.5, but our mean now becomes 0. Okay, the mean became 0. The standard deviation, one step standard deviation, became 1 because we said the properties of the characteristics of the standard normal distribution mu equals 0 and sigma equals 1. That's why you'll find here that mu equals 0 and the standard deviation from each side sigma equals 1 and sigma equals minus 1. Okay, I hope this is for the standard normal distribution. By having this one, we have now completed this theory part of the seminar number 5.